But now instead of cutting like this, I cut like this along the length. And suppose I displace this part of the crystal by the Burgers vector B and glue it back together again. Once again, there's going to be a linear defect, but that linear defect will be on the edge, parallel to the direction of slip, like this. This is what's called a screw dislocation. It's called a screw dislocation because if I imagine this to be a plane of atoms and I go around the dislocation, I will wind up on the same plane of atoms, but it's now been displaced down by the vector B. So as I move around the dislocation on a plane of atoms, I will just continuously transfer through the crystal in this way, like a screw. The modern example of that you see all around you is a parking garage. You get on a parking garage, go around, you're on the floor below, go around again, you're another floor below, around again. The axis of a parking garage is a screw dislocation. And that's the way you can kind of visualize this. When I notice what happens, how you can get slip from a screw dislocation. In the screw dislocation, you get it to slip. You want to move it perpendicular to itself this way. If I take this dislocation and move it into the unslipped region, what I will do, move it perpendicular to itself, what I will do is expand the region that has been slipped. If I move it all the way through the crystal, I will create one step, just like I did with the edge dislocation. In fact, the two configurations are identical. But in one case, I had an edge dislocation moving in this direction. In the other case, I had a screw dislocation moving in this direction. In both cases, I accomplished slip by moving the dislocation perpendicular to itself. There's another characteristic of screw dislocations. I mentioned in an edge dislocation, it moves very easily in the plane, but it's difficult to move it out of that plane. That's not true of a screw dislocation. In a screw dislocation, the Burgers vector and the dislocation line are parallel. And this has the consequence that you can move a screw dislocation in any direction, and it will move conservatively and do what it's supposed to do. So an edge dislocation has a well-defined slip plane. Screw dislocation does not. The fact that you see well-defined slip planes in low-temperature deformation is telling you that the dislocations that are important almost always have at least an edge component, so that they have a well-defined slip plane. Mixed dislocations. Most of the dislocations in the real world, if you go back, and I'll show you another picture in a minute, but you go back and look at the dislocations we generated in aluminum by making that indentation. They weren't long straight lines. They were wiggled and curved and gosh knows what all. In most real solids, particularly deformable solids, like deformable metals, the dislocations are not straight. They are curved in more or less arbitrary ways. And therefore, see, if the Burgers vector is perpendicular to the dislocation line, that characterizes an edge dislocation. If the Burgers vector is parallel to the dislocation line, that characterizes a screw dislocation. In most dislocation lines, neither of those statements is true. They are neither pure edge nor pure screw. They're what we call mixed dislocations. And the easiest way to see a mixed dislocation is to imagine a dislocation loop. In fact, many of the processes that create dislocations in ductile solids do create dislocation loops, circles on a slip plane. They look something like this. Well, now, if you go around the circle, right here and right here, the character of the dislocation is edge. Right here and right here, the Burgers vector is parallel to the line, so the character is screw. Everywhere else, it's neither edge nor screw. It's somewhere in the middle. So we call it mixed dislocation. And dislocations in real crystals are generally curved or looped. The Burgers vector, the thing you can say about them is that inside the dislocation, the Burgers vector is the same everywhere. Since the dislocation or dislocation loop was created by slipping an area. Remember, the dislocation is just the boundary of the area that's been slipped. So the characteristic of any dislocation loop is that the slip or the Burgers vector is the same everywhere. The region inside has been slipped by exactly the same amount, no matter where you are on the dislocation line. Mixed. So how do we describe the deformation that happens when this dislocation moves? If I make an arbitrary displacement of some section of the dislocation line, I can resolve that into a displacement that's parallel to the line and a displacement that's perpendicular to the line. The direction that's parallel to the dislocation line does nothing. If I take this dislocation and just rotate it and rotate it, nothing happens. Burgers vector doesn't change, nothing happens. The motion of the dislocation that is perpendicular to the dislocation, however, increases the area that is enclosed by the dislocation. Since the whole area that is enclosed by the dislocation is slipped by this Burgers vector B, then moving the dislocation perpendicular to itself, whatever its character, expands the area that has been slipped by the vector B. Do I show the whole thing? No, I don't. Suppose that I just let this, I should have another slide in here, I'm sorry I left it out. Suppose I just let this circle start growing, displacing it by the Burgers vector B. Suppose I let it grow as a circle, as a loop, until it comes completely out of the crystal. What will the result be? Well, the result will be this. Once that loop has expanded so that it covers this whole plane, the whole plane will have been displaced by the Burgers vector B, and it looks like this. So if we have an edge dislocation and move it through the crystal, we end up with this. We have a screw dislocation, move that perpendicular with itself, we end up like this. We take a circular dislocation and expand it perpendicular to itself, we end up with this. The dislocation is the boundary of the region that is slipped. When the boundary encompasses the whole plane, then the whole plane is slipped by one step. And it's really that simple. These things can look very complicated, but just keep that in mind. Deformation occurs when a dislocation moves perpendicular to itself. When the dislocation covers an entire area, that whole area is slipped by its Burgers vector B. When it sweeps out of a crystal, the crystal is slipped by that Burgers vector B. So that's the way that the deformation happens. There are a couple of things that are geometric things that are kind of important to know. Let's take a face-centered cubic crystal. If I look down on the 1-1-1 plane, the close-packed plane of a face-centered cubic crystal, incidentally, dislocations always move preferentially on close-packed planes for reasons that I'll tell you about later. The Burgers vector, if I have, let's let the bottom plane be A. So the atoms in the plane that's going to slip over the bottom are in B positions. This is a face-centered cubic or hexagonal crystal, so the A's, B's are on top of the A's. If I move by a lattice vector so that I can, in fact, glue the surfaces together without any displacement, then that would be a motion from a B site to a B site. This plane would slip so that this atom ended up over here, this one over here, and so on. That's a complete dislocation would give me that slip. But if you just take two sets of balls, two close-packed sets of balls on top of one another, you will discover that that's not the easy way to do it. If you're going to go from here to here, you have to climb over the edge of the A atom that's located right there, and it's hard to do. What is much easier to do, and I believe in the lab that there's a couple of close-packed planes you can just try this with. What's much easier to do is to do a zigzag, where the B slides to the C site and then back to the B site. Well, what can happen is the B atom can go to the C site and stay there, and that defines what's called a partial dislocation. In fact, in most close-packed materials, like face-centered cubic, like aluminum, the dislocations are actually two. We will have a dislocation that causes a slip B to C, and then a dislocation that causes a slip C to B. And these two partial dislocations will often be split apart because it's possible for them to split apart with a stacking fault between them. if this is an area in which the atoms are in C sites when they should be at D sites, that's what's called a stacking fault. And what you often see in materials, not so much aluminum, copper in particular, other SEC materials, is that the dislocations will be split into two partial dislocations separated by a stacking fault, in which the partial dislocations will give us deformation B to C and then C to B. Here we have B going to C. This area is all C stacking, so it's a stacking fault. Then with this dislocation, C goes back to B again. And that's what's called a partial dislocation. I don't need to say that much about them in this course other than to tell you what they are. Here's a titanium carbide with sodium chloride structure dislocation. If you look at these dislocations right there, for example, these are images of dislocations in a transmission electron microscope. You'll see that these dislocations are in pairs. And these are, in fact, partials. The region in between them is a part. The dislocation is split into pairs because these are partial dislocations. Focusing in more closely, this again just emphasizes that dislocations, some of these are partial, some of these are total dislocations. They're not straight lines. They wheel all over the place. And that's just the character of dislocations in real materials. The important thing is the dislocation carries a certain Burgers vector, and when it moves perpendicular to itself, it slips the material behind it by an amount equal to that Burgers vector. Again, finishing up, the macroscopic consequence of all this behavior is that when you stretch a material, you get slip along reasonably well-defined planes. Even though the dislocations may be wiggly and curved, their glide planes are well-defined because any curved dislocation has at least some edge character. And an edge dislocation only moves easily in that well-defined glide plane in which it can move conservatively, as we discussed way back here. Even a little bit of edge character will cause the dislocation to be rather planar in its slip. So even when we do macroscopic deformation, the macroscopic deformation, if it's done at low temperature, tends to leave well-defined slip planes behind. And that's what you saw in this picture right here. This happens to be stainless steel, which is FCC, austenitic steel, tensile direction, well-defined planes over which slip has occurred to cause the overall deformation. Well, I'm going to stop there for today, I think, yeah. And we'll do a little bit more. We'll kind of review this on Friday and then move into the other kinds of defects, the surfaces and the volume defects. Okay? I spoke a little faster than I meant to today. I got through the material more quickly anyway, which means I probably talked too fast, so we'll slow down a try. This is one of the tougher concepts in material science for most people to grasp, the idea of a line defect or dislocation. It's worth spending just a little bit of time on because it's an enormously important concept, and once you do get it clear, it stays clear for a long time. So, okay.